All right, so now we're going to move on to lesson 2.4, which is on factoring and solving polynomial equations. So we've talked about factoring before when it was just quadratics and we wanted to factor down to x plus something, x minus something, and that was it. So we've seen that with our general trinomials. Now we're going to take a look at some of the other possibilities with larger factors. First thing we need to understand is, what does the definition factored completely mean? So, according to your textbook, a factorable polynomial with an integer coefficient is factored completely if it is written as a product of unfactorable polynomials with integer coefficients. So a lot of that is going to be more easily understood when we can see them as examples. So there's a couple of examples there. So take a look and see. The big one is showing at the bottom, 3x times x squared minus 4 is not factored completely, since we can continue to factor x squared minus 4. And then you'll see the previous example where 5x squared times x squared minus 3 were factored completely, since x squared minus 3 cannot be factored any further. Let's look at an example. Being able to find a common factor is going to help you out quite a bit. So our first example is x to the third plus 12x squared minus 15x. So obviously they all have the factor of x. So take that out and you're left with x squared plus 2x minus 15. And then you would factor that quadratic just like you normally do. So we factor the trinomial and it becomes x times x plus 5 times x minus 3. The next example, 2y to the fifth minus 18y to the third. So we're going to find that common monomial factor, which would be 2y to the third. And we're left with y squared minus 9, which is a difference of two squares, so we can factor that even further. And then our last one, 4 times z to the fourth minus 16z to the third plus 16z squared, means that the common factor is going to be 4z squared. Take that out and we are left with z squared minus 4z plus 4, which is a perfect square trinomial. So we can write that as 4z squared times z minus 2 squared. So we're just taking out that common factor first and then factoring the trinomial just like we have done since the beginning of chapter 1. Let's take a look at some special patterns though. If we can start to recognize this, it's going to make our life much easier. So the first one is the sum of two cubes. So if you have a to the third power plus b to the third power, then it would simplify down to a plus b times a squared minus ab plus b squared. Notice that because it's missing that 2 in the middle, it's not 2ab. This is not a perfect square trinomial. It's almost there though. The difference of two cubes is similar. We're going to subtract a minus b and multiply that by a squared plus ab plus b squared. So this is an area that, again, memorizing this is going to help you out infinitely. There really isn't an easier trick to get around not knowing the special factoring patterns. All right, so let's take a look at how this would work for us. So we have x to the third plus 64. So we're used to recognizing 64 as the product of 8 times 8 being a perfect square. But it's also a cube, a perfect cube, 4 to the third. So if we recognize it as x to the third plus 4 to the third, we have our a and our b. So then we can go into the form and say that it's equal to x plus 4 times x squared minus 4x plus 16. All right, here we have 16z to the fifth minus 250z squared. So step 1 is we're going to factor out that common monomial, and we're left with 8z to the third minus 125. So 8 is a perfect cube, as is 125. What I'd recommend doing is creating a chart of some of the first 12 perfect cubes, and then if you're looking at what you think might be the sum or the difference of two cubes, you can always use your calculator to find the cube root. So we recognize the pattern is 2z to the third power minus 5 to the third power. So we can follow our special factoring pattern in order to get what 8z to the third minus 125 factors down to. And of course, remember that at the beginning is 2z squared. Remember that at any point in a lesson video, you have the power of being able to stop it and copy down whatever information you need, or go back and rewind and re-listen to something. So if this is going too fast, you get to control how quickly you hear it. All right, let's take a look at another commonly used example, which is factoring by grouping. So when we factor by grouping, we're looking at something and we recognize, there's no easy way to take out a common monomial. So what can we do instead? Well, we can start to see if there's any patterns between the first two terms and maybe the last two terms, and we factor them. So I would put x to the third minus 3x squared in one set of parentheses, and then negative 16x squared plus 48 in the other set of parentheses. And in the first term, I could take out x squared, leaving me with x minus 3. And in the second term, I could take out negative 16x, leaving me with x minus 3. So now you see that we have a common factor between those two that I can then take out of the distribution problem. So I take out that x minus 3, and I'm left with x squared minus 16. A difference of 2 squares means I can just factor that even further. And so now I'm at my final factorization. All right, let's take a look at another example. So if it's in quadratic form, what we're going to want to do, an expression of the form au squared plus bu plus c, where u is any expression in x, is said to be in quadratic form. So this factoring technique you've studied in previous chapters can be sometimes used to factor these expressions. So we have 16x to the fourth minus 81. Well, if we were to write that as a difference of 2 squares, we would have 4x squared being a and 9 being b. So then we are then left with 4x squared plus 9 times 4x squared minus 9. Well, I can't factor out 4x squared plus 9, but I can factor out 4x squared minus 9. So a difference of 2 squares once more. So then I'm left with 4x squared plus 9 times 2x plus 3 times 2x minus 3. And I have now factored it completely because I can't go any further. All right, let's take a look at this one. 2p to the 8th plus 10p to the 5th plus 12p squared. Now, first thing I would do is I would take out 2p to the squared actually. So then I am left with p to the 6th plus 5p to the 3rd plus 6. And I'm going to treat this like it was a quadratic. That p to the 6th could be the same thing as saying p to the 3rd plus or minus something times p to the 3rd plus or minus something. So when I factor that out, I get p to the 3rd plus 3 times p to the 3rd plus 2. Remember that when we have exponents, when we multiply exponents, multiply our powers, we add the exponents. So p to the 6th, we're not taking the square root of that. We would just divide it by 2 to get my 2 factors. So it's a little bit tricky and you're going to need some practice. So make sure that you are taking a look. In your textbook, there's a lot of guided practice questions that you can try on your own, and we can review those in class tomorrow. All right, let's take a look at our word problem. So for the city park, it says you are designing a marble basin that will hold a fountain for a city park. The basin's sides and bottom should be 1 foot thick. Its outer length should be twice its outer width and outer height. What should the outer dimensions of the basin be if it's to hold 36 cubic feet of water? So notice that our picture is showing us that the width and the height are x, and then the length is 2x. And then the dimensions would be 1 feet. So the width of the overall going around is 1 feet. All right, so the volume is going to equal 36, and we're going to have the interior length, the interior width, and the interior height. So we're having to subtract for the thickness of the basin. So that's where the -2 is coming from. And of course, the height only has it on the bottom, not the top. So we're going to write out the equation, put it in standard form. And so now we are given 2x to the third minus 8x squared plus 10x minus 40. So we're going to factor by grouping. We can take out 2x squared in the first part, and we can take out 10 in the second part. So when we remove that, we're left with x minus 4 in both groups. So that's our common factor. Move it off to the side. And we're left with 2x squared plus 10 on the other one. So we're going to set the equation, each factor equal to 0. Now, since we're dealing with the real world, when I set 2x squared plus 10 equal to 0 and try and solve for x squared, I'm going to end up with a negative number inside the radical sign, which means there is no real solution for that one. But x minus 4 equal to 0 means that x is equal to 4, so that we can then substitute that in back into the original dimensions for the outer part of the basin. And that's it for this lesson. Again, at any point, you can always go back and review any of these examples as you wish. And always, I highly recommend following along in the textbook so you can see it more clearly for yourself. I'll answer any questions you have in class. See you next time.